Okay, so welcome to this part of Tech Topics Thursday. Uh, a few weeks ago, I presented an introduction to the electronics course. We're going to start off with Module 1.1, circuits and components, and there'll be quite a few other modules, and we're probably doing one per week. This one's going to be fairly long, but the others are going to be maybe 5 or 10 minutes or 15 minutes at the most. So today we're going to talk about electricity, conductors, insulators, circuits, components, uses, schematic diagrams, and then we'll look at a circuit as a demo. So there's basically three learning approaches you can use. Watch it and ask questions. You can do it by online, and we'll be looking at some tools in a couple of weeks, or you can do by building it. And people have said that electronics is 50% lecture and theory, and then the real fun is experimenting and trying different things. Um, so all of you are seeing the PowerPoint presentation, right? All right. I'm assuming so. So
Yep.
electricity is basically the flow of electrons in a closed system. And what some people have difficulty in understanding is that electricity is a closed system, while like water flowing in a pipe is, potentially an open system. So you need a closed system for it to work. We use conductors to transfer the electricity around. We're not really sure exactly how it works. A few years ago, people were thinking that it's like electrons flowing in a pipe. You put electrons in at one end and they come out the other end. Now they seem to think it's more like a chain in a pipe that vibrates back and forth. So at one end, the source of electrons is causing the other electrons to vibrate back and forth like a chain, and then the other end vibrates. But exactly how it works, no one's 100% sure because we can't see the actual electron flow in the cable yet or in the wire. But one thing we do know is the skin effect. So DC tends to flow on the inside of the conductor, and RF tends to flow on the outside of the conductor. And as the frequency goes up, more tends to flow on the outside of the conductor. So basically, a circuit is a closed loop consisting of conductors and components. And we'll look at the various components coming up. The flow of it should be the flow of electrons is current, and the electron flow from one potential difference to another potential difference is voltage. We'll look at current and voltage in more detail when we talk about Ohm's law. So a conductor allows the flow of electrons, is made of metal, copper, aluminum, gold, or silver. If it's a wire or cable, it's surrounded by insulation, which is the color part here, and then this is your copper. And then if you have more conductors put together, you form a cable. Or you also have a coax cable, which we use typically in RF, where here's your copper wire, here's your insulation, and then you have a copper mesh surrounding the cable, which keeps out interference from other signals. And we'll be looking at transmission lines and antennas towards the end of this course. And it's also low value of resistance. So we'll be talking about resistance again in a few more talks from now. And the opposite of a conductor is a semiconductor. Is an insulator. There's also a semiconductor which sometimes allows the flow of electrons and other times not. And these are used in transistors and diodes, and we'll be talking about those too in 3 or 4 weeks from now. So an insulator does not allow the flow of electrons. It's typically made of glass, porcelain. Oops, this should be This should be plastic. Here's some examples of insulators. These are used for fences, for example. And here is a big insulator that they use on a power line. And the person is fixing an insulator on one of the high voltage power lines. Now, a circuit is basically a connection of various parts together. So you basically have three ways of representing a circuit. One is to have a picture of it. So here's a battery and a battery holder. Here's a lamp and a lamp socket. And here's a switch. So that's a picture part of it. You can also draw it as a diagram. So here, again, you have your battery down here, you have your light bulb up here, you have your wire connecting all of it together, and here you have a switch. More commonly, you have a schematic diagram, and you have a symbol for the battery, a symbol for the lamp, and you have a switch, for example. So these are different ways you can represent a circuit. And as simple circuits you can do by picture or by diagram, but as things get more complicated, it tends to be a schematic diagram. Now you have different types of circuits. You have an open circuit, which basically means it's turned off. You have a closed circuit, which means that it's turned on. And then you can also have a short circuit, which provides an abnormal, dangerous situation. And we have examples coming up here. So an open closed circuit is basically normal operation. So you have your battery again, you have your light bulb, and if it's a closed circuit, you have current flowing from your battery through the light bulb, and the light bulb lights. So that would be a closed circuit. Now, if you had a switch in here, for example, or a break in the wire, you would have an open circuit because there's a gap here and the electrons can't flow across the gap, so the light doesn't turn on. So this would be an open circuit. So if, for example, you have a circuit here and you take a piece of wire and you jump this across here or here, you have a short circuit. And you have to be careful with the short circuit because you have a lot of current flowing from the battery or power supply, and it can heat up the cable or the wire and can catch fire, or also, there could be the battery could discharge and heat up and the battery can actually explode. And, here, for example, is a circuit, and, if there's a short circuit here, they have a fuse here, and the fuse will then melt and then prevent it from causing more damage. So we'll talk more about fuses when we talk about amperage and about resistance in a few weeks from now. So there's a number of different ways you can draw a circuit, and it requires a closed loop. So you can have like an output to an input. So this could be, for example, an electrical outlet that you have on your wall. This could be like a fan or an electric heater or a lamp that you plug it in. And, so you have an output, you have some wires connecting to the input of the lamp. So this is one way to represent it. Another way to represent it is to have an output of something, like this could be a radio or a signal generator hooked up to your device. This could be a filter, it could be a bunch of resistors, and then you're feeding it into an input of something. So this could be like an oscilloscope or a meter, and again you have two wires connecting it all together. Now, sometimes it may appear that you only have one wire connected. And this is when you use the concept of grounding. So you have an output here, let's say a battery or a power supply, and you ground one of the things. You have an input, like this could be a meter or an oscilloscope, and it's also grounded. And then the device you're testing could also be grounded. And so it appears, you only have one connection, but you'll have the return loop going through the ground. So this is another way you might see it on some schematics, and it might look like only one wire is connected, but you have a ground. The next thing that's important to remember is series and parallel circuits. And a series circuit is basically when you have things connected end to end. So here, for example, are two light bulbs connected end to end. So, you've got one battery here connected to one end of the light bulb, this end of the light bulb being hooked up to this end of the light bulb, and then this going back to the battery. So this is an example of a series circuit. And the other way of doing it is to connect it back and forth. Here, for example, are three light bulbs, and these three light bulbs are connected in parallel, and then the power source is coming from your AC outlet. And here is a representation, a battery and two light bulbs in parallel. And when we get to Ohm's law, we'll be studying what happens to the current and to the voltage in a series circuit and in a parallel circuit. And then as we go on in the future talks, we'll be talking about resistors in parallel and series, capacitors in series and parallel, and also inductors in series and parallel. So this concept is important to know, what the difference is between series and parallel. So next we're going to talk about components. We're going to talk about power sources, resistors, inductors, capacitors, diodes, and transistors, and tubes. So this is just going to be an introduction into these 6 different types. We're going to spend the whole talk on AC power and a whole talk on DC power, probably 1 or 2 talks on resistors, 1 or 2 on inductors, capacitors, and then probably 2 or 3 sessions on diodes and transistors, and maybe 1 on tubes, and then we'll combine these things together into different circuits, and we'll be spending time on that. So these are your basic components. So let's take a look what they look like. So for your power source here, this is a typical battery. If you look at a resistor, these are color coded and of different sizes, meaning different power levels or wattage. And we'll get into that when we talk about power. If we're looking at an inductor, it's basically a coil of wire. It could be a wire mounted around a toroid. This is quite common for anons and balance that we use in radios. When we have filters, we can have it again wound around a toroid. You can have one that's covered up with plastic, or you can have something like this. And you can also have them wound in air with no toroid ferrite material here. So we'll be exploring all the characteristics of that. A capacitor looks like this. They come in various shapes and sizes. The bigger ones are typically electrolytic capacitors that are used in power supplies. Here are some smaller electrolytic ones. These ones are variable capacitors, often used as a tuning knob in radios, where plates move in and out, and that varies the capacitance. Here are some disk capacitors, and these are typically used in your different circuits, and they come in different values, and we'll explore that in more detail. Here's a pass-through capacitor. If you're trying to separate one part of a circuit to another part, you may actually put the power supply or a signal through one of these capacitors, feed-through capacitors. They're not used that often, but this is an example of one. And then we get into diodes and transistors, and typically all of these so far have only had 2 leads. A diode has 2 leads, but a transistor has typically 3 leads. And there are smaller ones here and the bigger ones here, and then this one can be used with a heat sink. So we'll be spending a lot of time talking about your bijunction transistors, the MOSFETs and different types. So there'll be more coming on that. And then what started it all off is a tube. We'll talk a little bit about tubes in the future too. They're not used that much anymore, except for some high fidelity audio amplifiers, and then also for some high power RF amplifiers. If you're talking about 500 watts, 1500 watts, they may still use tubes. So we'll talk about tubes in the future too. But this is how it used to look like. Nowadays, before I get into what they look like now, we'll also be spending some time on power sources. So direct current is battery, solar panel, a wall wart, or generator. And we'll have a whole talk on this, and then a whole talk about alternating current. These could be transformers, alternators, signal generators, or a radio transmitter. And, today, all these components, they used to look like this, where you could actually tell what they are, and they're, fairly big to handle, and you could actually see them. Nowadays, they're getting to surface mount components, and here are some integrated circuits. Here might be a transistor. This could be maybe a crystal or a coil. These could be capacitors, resistors, or inductors, and they're becoming smaller and smaller and smaller. And they even got smaller ones now that are about the size of if you take your pen and you draw a dot on a piece of paper, that's how big they are. So you can probably work with 805s and up, but once you get smaller to 805s, it's pretty difficult to solder them or even handle them. And they tend to have wings and fly all over the place too. So if you'd ever dropped one of these things down in the carpet or something, you'll probably never find it again. So all of these are placed on circuit boards with a robot now and soldered on, also using like a soldering oven or things like that. So it's all done by robot. And that allows you to manufacture a lot of parts in a very small scale. There's a whole area of electromagnetics. So you start off with magnets, and then when you take the inductor and the wire and wind it around something, you tend to form an electromagnet, and you can use these as a relay, which is like an electrical switch, and then solenoids, where it's like a piston moving in and out of a coil. And these are used for electric valves, like a solenoid valve, if you want to turn on and off your sprinkler system, for example, or your garden, watering. You probably have an electric valve. Also, all your doors that have an electrical lock on it probably have some sort of solenoid. Then there's the transformer and motors, generators, and alternators. And we'll get into how all of these work in future presentations. So, electronics is changing. And, 10, 15 years ago, it used to be point-to-point wiring. And this used to be, fairly easy to do, but it was also very labor intensive. And that's where, for example, Heathkit was very popular, back in the 80s and 70s and 80s, because people could buy kits and they could save money because you weren't paying someone to actually make all these connections and solder all these things in place. So it was really economical to make kits. Then came the integrated circuit, and here's one like an 8-pin integrated circuit. This could be a timer, for example, or an operational amplifier. And next thing came PCB boards. Here is a simple one. So a lot of these components now are mounted on a PCB board with connections going back and forth. These used to be through hole where they actually had holes going through them. So this component here would have, 8 holes, and you would have 8 holes on the board. Now with surface mount, you don't need holes anymore in the board. You just put them on top, and you kind of various layers of copper running back and forth. So, the big thing these days is to have modules like this. So you might have like a relay module as, for example, and then you would hook this relay module up to a microprocessor. And, this is a small PC board. Here's a big PC board. Probably a computer or so, and then you've got this is probably a CPU or some type of memory chip, where you might have, I don't know, probably a couple hundred connections coming out of it. And, here's one with a fewer connections. And so now, they are coming out with microprocessors. Here's, for example, a Raspberry Pi. You have your in and output pins here. You have your Ethernet connection here. You have your USB connection here, your USB-C connections here. And then the other thing is you have also the Arduino board. And, these are different Arduino boards with different number of I/O pins, memory, different chips for computers, come in different sizes. So nowadays, rather than doing something like point to point, they would hook up, they would program one of these computers to do it for you and have one of these input output modules. So we'll start off with point to point wiring, and then in our future courses, we'll actually do some programming of Raspberry Pis and Arduinos. So why do you want to put all these components together? Well, they'll have various functions depending on what you put together. They can be an amplifier, they can be a radio, it can be a transmitter, a mixer, modulator, a converter to convert digital to analog or analog to digital signals. And you need this for your microprocessors. You can have a low pass filter, a high pass filter, or an antenna tuner. You can have power supplies, AC, DC, and we'll be spending on some time on, how a power supply works. And then also you can have various test instruments. So that's why we put components together. And again, things are changing. So, 10, 15, 20 years ago, we used to do hardware design, and we used to build, this is called prototyping. You would have holes here and you would connect things together, try it out, see if it works. If it worked, you would make up a PCB board, and, you would drill holes through it, make this board, put your components on it, solder them on it, and that's your circuit. These days you have your Raspberry Pi here, for example, and you have your various hats that you stack on top of them. And then each one of these hats can perform a different function. And here's for an example of a Raspberry Pi connected to various different modules. And all of these modules do different things, and you run wires back and forth. And basically you program the software and your microprocessor to do, to turn on a light or to dim a light. So, that's the way it's done these days. So we'll spend some time on electronic circuits so you get to understand how they work. And then we'll end up doing some programming in future courses. And then one of the things for schematic diagrams, there are different ways to represent various things. Here, for example, is a resistor. Here is different types of switches. Here's what a capacitor could be. Here's what an inductor might look like. Here's what a source could look like. And then semiconductors like transistors, MOSFETs, JFETs, and we'll be talking about all of these in future things. And then when we take in the second module, which is more geared toward the advanced qualification course, we'll talk about logic gates, and here's just some examples of different logic gates, and we'll do some experiments on those. And the other thing I wanted to talk about was you'll hear the term active and passive circuits. It's not used that much anymore, but basically a passive circuit doesn't require an external power supply, uses part of the signal to do whatever it needs to be done, and usually you get some sort of signal loss. So here are some examples of a low pass filter. And a low pass filter basically consists of a resistor and a capacitor. And when we do the section on filters, we'll actually be building one of these, and we'll use a signal generator and an oscilloscope, and we'll look at the input and output of what it looks like. But basically, it's a resistor and a capacitor. You're going to lose some of the signal here across the resistor. So you're going to have some signal loss with this circuit. Now, if you looked at another low-pass filter, this is typically in the audio range. You tend to use an amplifier. So this is an operational amplifier, and we'll be talking about operational amplifiers in the advanced Module 2 course. But, you have the voltage coming in, you have a couple of resistors here, a couple capacitors, and because you are using an amplifier, you can actually get more output than input, or have it equal, so you're not going to lose any signal. So here, here's your low pass filter, and then your signal's going to come off. It's going to allow the low pass signals to go through, and then the higher frequency signals are going to be dropping off. So this is the active and passive circuits. Components put together form circuits that gives you functionality. There's only a limited number of components. I think when we looked at it, there were 6, but you can put them into many combinations and build anything that you want to. So, any questions so far? We'll do a little demo coming up next. And next week, we'll talk about mathematics, just to introduce you into some graphs, some variables, some exponents. And then the week after, we'll be talking about units and the metric system. And then we'll get into knowing Tinkercad, which is an online simulation program. And then the following week, we'll get know your multimeter, and then we'll start getting into resistors and Ohm's law and measuring current and power and things like that. So any questions before we go on to the demo? So here's a bonus question. Why does the motor not run? So let me just stop the share and bring up my camera. So let me go to here. Okay, you should all see the camera now. So let me bring over the circuit. So here is the circuit from one of the kits that you could buy at Canadian Tire. And let me just take out this for now. And we'll be using this one quite a while because we're gonna take it apart, and we're gonna measure current, we're gonna measure power, and we're gonna measure resistance. So this is a very basic one. You start off with two batteries. Two batteries are actually in series together. So 1.5 volts and 1.5 volts give you 3 volts. So after we do the multimeter session, we're going to actually do some measurements of this and measure the voltage. Then, you have either the positive or the negative coming out. Usually the negative is grounded, but for this demonstration, I've put all the controls on the negative side and just made the positive side connect through. So you can take this apart, like, now it's an open circuit, and we're going to hook up, for example, an ammeter here and measure it. So Then you come out here. You have two switches in parallel, and you have a resistor here, and you have an LED diode. So these two are in series. So I can press the button here, and the LED will come on. Or I can move the slide switch over, and then the LED is on until I turn the slide switch off. So, and then the other thing is, I've got here basically a cable with an alligator clip at the end. So, I mean, I could take this and I could connect, this over here, and the LED will come on because I'm bypassing the switches here with this. I can also, for example, bypass the resistor, and the LED will come on. Just a second. I'll have to press the button. So the LED comes on even when I bypass the resistor. And we'll look at why the resistor is actually in there in a future thing. So here is a motor. And if I put the motor here, for example, if I put the motor here, for example, we'll learn two things. One is it depends on how you hook it up. So you won't, unfortunately, you won't be able to see the rotation of the motor, because it looks, if it's going clockwise or counterclockwise, it looks the same on the camera. But you can tell which way it's going, whether this thing flies off, and whether I can find it or not. So when I press this, it starts, and you can see it's going, and the light turns on, and the motor's running. Okay, so this time it didn't fly off. So if I just reverse the motor and put this thing on again and press the button, it'll rotate in the opposite direction. But when I turn it off, the red thing will fly off. Oops. And that's the only way I can show how the motor rotates, because it looks the same on the camera. But the interesting
That's
thing,
pretty funny, Roy.
Pardon me?
That's pretty funny, Roy. I like that.
But the interesting thing is, I put the motor here and it runs. But if I put the motor here, where right here, and Richard, you can't, you can't answer the question. But how come the motor doesn't run, and how come the light doesn't turn on when I put it here? We'll explore this further on as we get to it. Well, if I put the motor on the other side of the resistor,
I bet. Oh, it's the resistance is high probably on the resistor.
We'll be exploring it in detail when we
Because it
actually
doesn't
do
go
some
through
measurements. Like here, the
that
motor
loop.
turns and the light comes on.
This is very nice, this setup, Roy.
So this is what the circuit looks like in the picture. Now,
This is very good.
Now, when we take it away and go to the real whiteboard,
They should have this in our high school.
this is what the circuit looks like. So
Your circuit is messy.
Well, it's hand drawn.
I'm just making fun of you.
It's a whiteboard. It's a whiteboard.
I know. Now,
bring back the other circuit.
So, you've got your two batteries here. This is a representation of a battery. Here's a representation of the push button. And here's the representation of the slide switch. Here's your resistor. Here is your LED. And here is your motor that we were playing with. Now, there is some unknown device in here, which we don't actually know what it is. But we're gonna, in one of the future classes, we're gonna build an octopus, and we're gonna hook up the octopus to it and look at it with the scope and the octopus and see if we can actually figure out what this device is. So this is what a circuit looks like. So we'll be spending a lot of time with this simple circuit, measuring voltages, measuring power, and measuring current. And then as we progress, we'll start introducing transistors and other things into this circuit. But we'll start off with something simple as this, and we'll take it apart and do a lot of measurements once we do our session on the multimeter. So next week is mathematics, which should maybe only last about 10 minutes or so. And then the week after that is about units and the metric system, which should be only about 10 minutes or so. And then after that, we'll get into Tinkercad. That'll probably be about 15, 20 minutes. And then the following week after that, we'll be doing getting to know your multimeter. Just looking at various multimeters. What are the inputs, outputs? What do they measure? And then we'll start getting into resistors, power, and voltages and things like that. So, any questions about that?
Where did you say you got that, Roy?
Canadian Tire.
Wow.
It's
Or
called
online, I guess, huh?
no. They have it in the store. They had them for sale at Christmas. It's called Elenco, E
Really?
L
That's
E L
that's a
E N
great.
C O, and it comes in different kits. You can, one of the kits actually allows you to build a radio. Other ones are more geared to
Oh, that's
light
a smart
shows,
gift.
motors, and stuff. So we've got a whole different. I've got a
Yeah,
whole kit of those.
that
So
is
let
a
me
smart gift for kids. It's really,
so
really.
so let me just stop the recording. But I don't see the recording thing. Maybe we
No,
didn't.
oh,
Oh
well,
no,
it's
it's up
red.
here. Yeah, I see it.